Okay, now that we sort of know how to evaluate logarithms, let's look at graphing a logarithmic function f of x equals log base 2 of x, or if you'd like, y equals log base 2 of x. Now in graphing this, I would need to probably make an xy chart to get an idea of what the graph looks like. Now notice we talked about the exponential form and the log form of a logarithmic function, so why don't I go ahead and put this in exponential form. If I have log base 2 of x is equal to y, or my function, I can do the circle, and if I do that, I'm going to end up with something probably easier to evaluate. 2 to the y is equal to x. That might be easy to fill my chart with rather than evaluating a bunch of logs. Remember, at any point if an equation that has logarithms in it can be changed by using the circle, it might be easier to evaluate it. So if I go punch in a bunch of y's or plug in a bunch of y's, I can probably get the x's easily. Let's say I have -3, -2, -1, 0, 1, 2, 3. So I'm just going to go ahead and input those y values, and in the process I will have the corresponding x values. Again, I'm using the exponential form to figure out these values because I'm used to this more than the logarithmic form. So let's go plug those in. So once I worked with the exponential form of this logarithmic equation or function, I put in these exponents and I got these values and I made them into ordered pairs. So I have 1, 2, 3, 4, 5, 6, 7 ordered pairs that I'm going to go graph and try to get an idea of what the graph of a logarithmic function looks like. So notice as I plug in my, or as I plot my ordered pairs, I have 8, 3, 4, 2, 2, 1, and then 1, 0, and then halfway and down 1, a quarter of the way down 2, and an eighth of the way down 3, and it looks like so I have my ordered pairs plotted, and I'm going to go connect them with a curve, of course. And when I connect them, I make sure that the y-axis is not ever crossed because it looks like the x-coordinate never becomes 0. I keep putting in these y values, and the x values will get smaller and smaller, and on this side they'll keep bigger and bigger as I go to the right, but they're never going to reach 0, so this actually has a vertical asymptote on the y-axis, which should remind us a lot of the exponential equation we were looking at. So this has a vertical asymptote, which is actually the y-axis or the line x equals 0. Also pay attention to the domain and the range of this. It's kind of going to remind us of the exponential function. Again, the domain is only the positive x's, so from 0 to infinity, and the range is all negative y's because the graph keeps going down and down, and also all positive y's because not only does the graph go to the right, but it slowly goes up as well. So the range covers everything, but the domain is only the positive x values. And this should remind us again a lot of the exponential function we looked at. So here's what I mean. Let's look at this guy right here, which is really the graph is right here on the right, and it looks like an exponential function, but it actually came from my log equation here, because remember these two were equivalent after I did the circle. Now if I want to find the inverse of the log function, which is right here on my right, I just have to switch the x and y. So here's my log function, log base 2 of x is equal to y. My function's other version, after I did the circle, is really 2 to the y equals x, and now if I want to, if I just take and I switch the x and y into this one, for example, I'm going to get a function that I'm familiar with. 2 to the x equals y. And this is really the inverse, because I switched x and y is already solved for. This is really the inverse of this function that I started off with, that I had switched into exponential form. So these two guys are inverses of each other, which means all logarithmic functions have their inverse exponential functions. And if I were to graph this guy up above over here, let's go graph it. All I would really need to do is switch these x and y values, because remember how we get inverses of each other. I just take the ordered pairs and I switch them, and it gives me a reflection about the line y equals x. So I'm going to go switch all these ordered pairs to get my graph for my exponential function. So here's what I did. I took my log function that gave me these ordered pairs. Notice whatever values I put in, like if I put in an 8 for my log function here, log base 2 of 8 will spit out a 3 accordingly, even if I want to deal with it in this version and not in the exponential version. Or if I plug in a 4 in here, log base 2 of 4 says what's the exponent of 2 to get to 4, and that would spit out a 2. So I could still plug in all these x's and get all these y's into this highlighted version. And then once I get those ordered pairs, or the way I did it earlier, I just take those and I switch them, and that'll give me the inverse function of log base 2 of x, which is actually 2 to the x, which we found over here by switching the x and y's. So to get the inverse graph, I just switch these ordered pairs, I graphed them, and we got the familiar exponential function that we had looked at before, and this is my original log function, and notice that mirror in the middle that causes them to be reflections of each other. So we want to make a note of that logarithms and exponentials are inverses of each other. So in other words, if I'm given log base 3 of x as my original function, its inverse will just be the exponential function 3 to the x, and they will look like this when I graph them, mirror images of each other across the line y equals x. Or if I give you log base 10 of x, where I'm putting in the 10, and usually you'll just see log of x maybe, you'll probably see it more in this version without the 10 written, then the inverse of that will just be the exponential function 10 to the x. So logarithms and exponential functions are always inverses of each other, and these bases will match when you're looking at those inverses. Now another piece of info that we want to keep in mind is that since two inverses undo each other, we get back to where we were when we started. For example, if I am at home and I go to work, this will be my function. If I apply the inverse, I'm going to get back to exactly where I started, which was home. So if I apply the function, I get to work, and then immediately if I apply the inverse, I get back home, which is where I started. For that reason, whenever you compose two inverses, you're going to land back exactly where you were originally, which was x. So f of f inverse of x is going to be the same as f inverse of f of x from function compositions, which is going to land me back at x. So, and further, since f of x log base a of x and f inverse of x, the exponential function a to the x, since these guys are inverses of each other, if I compose the two, meaning if I plug this inside of this function, or take this whole function and plug it inside the log function, I'm going to get back to x, where I started, by doing these two function compositions. So they give us more properties. Property 1 says that log base a of a to the x gives me a value of x. In other words, if your base and your argument's base are the same, the answer that plops down is always just an x. Or if your base and the log's base are the same, the answer that pops down is always just an x. And these help us evaluate some more logs without having to deal with a calculator. Okay, let's evaluate some logarithms. I have log base 2 of square root of 2. So I'm at 2, and I want to get to square root of 2, and I'm trying to guess what the exponent is. Well, I can do the circle with this one if I want to. I can say, hey, I don't know what this equals to, so I'm going to go ahead and do the circle and say 2 to the what gives me square root of 2. And remember, square root of 2 can be rewritten as a fractional exponent, which is really 2 to the 1/2. So my answer, or my exponent in this case, my question mark, is really just a half. So it looks like log base 2 of square root of 2 is just equal to 1/2. That's one way I can look at that problem. Or I can maybe use one of these inverse properties without having to do further analysis, I can say, well, log base 2 of root 2 is the same as log base 2 of 2 raised to the 1/2. Because remember, the power of a radical is really an exponent of 1/2. Now, since I have the bases to be identical, inverse property says my answer is just the 1/2 that pops down. Same thing for part B. I can say, well, I'm going to do the circle. I don't know what this equals to, so I'm going to say 7 to the what gives me 7. Well, the exponents must be a 1 if these two items are to be equal, because there's nothing involved other than an exponent of 1. So my answer must be 7 to the 1 gives me the 7 that I was looking at. Or just like the first case, I can say I'm looking at log base 7 of 7, and what is that equal to? Well, I have the same base here and the same argument here, and the invisible exponent is 1, so the answer must be just 1. Again, I'm making use of property 1 of inverses, where the bases are the same and the exponent just pops down. Part C says 5 raised to the log base 5 of 11. Now, log base 5 of 11 can't even really do it on my calculator because it's a base 5 and I only know how to use base 10 as of right now. But I do notice that this base and this base are the same, and the inverse properties up above said that if the big base and the little bases are the same, then it just takes you back to x where you started. So I can use that shortcut and say the answer that plops down is just 11. Same thing for part D. Notice if a log doesn't have a base, we said automatically the base must be an invisible 10, because it's a common log. So since this base and this base are the same, the answer that pops down is just a 9. Let's look at log of cube root of 100. So, of course, this must be an invisible 10. I'm going to put that there first. And then I'm going to think of cube root kind of like I thought of the square root here and see where it gets me. So we're going to say that's going to be log base 10 of really 100 raised to the 1/3. So cube root is really a 1/3. And then we know how to deal with this guy. That's just going to be a 10 squared. So again, I'm going through this process because I want to have maybe matching bases so that I can have my answer pop down. So I changed 100 to 10 squared, and I changed the cube root to a 1/3. Now, since I have a power raised to a power, remember properties of exponents say that when you have a power raised to a power, you can simply multiply them. So I have log base 10 of 10 to the 2 times 1/3 is just 2/3. So this exponent is 2/3. And finally, I can use my base and base are the same, and the inverse property says the answer that pops down is just 2/3. So without using a calculator, we know that log base 10 of cube root of 100 must be 2/3. Let's do a quick recap of what we talked about with logs. Logs spit out exponents. That's the first main thing. In other words, 5 to what power gives me 25, and the power or the exponent is 2. Next, we can use the idea of do the circle if we want to switch back and forth between the log form and the exponential form. In other words, this guy in log form would be log base 3 of 9 is 2. Or this guy in exponential form would be 2 raised to the negative 3 gives me 1/8. So I did the circle again. Then we said logs and exponentials are inverses of each other. So that if my function is 5 to the x, its inverse will be log base 5 of x, or vice versa. I could start with this and have that be its inverse. Logs and exponentials are inverses of each other, therefore their graphs can be obtained by switching their x and y values. And last, we had the inverse properties, which pop out the x's.